Good, perfect.
Okay. So hello, everyone. I'm also from Seoul, Korea. I'm a professor at the Seoul National University of Science and Technology. And today I will give a talk on the research we've done, which is to use deep learning approaches to automate the classification of BIM elements. And this is continuing research. So we're trying to enhance what we've done before by augmenting the data and also using a technique called semantic segmentation. Okay, just to give you a background for the motivation of our research, one is that, as you know, BIM has been with us for a very long time. It is not a new technology. With the growth of BIM, we have more and more specialized tools and applications that do very specific activities or analysis that we need to do the design and construction using our BIM environment. So with all these tools, it is important that we have a information or data standard and a format that we can all agree on, because without such a standard, there would be too much paired export and import features, which really undermines the initial objective of using BIM as a single information protocol. So fortunately, what we have today is what we call the Industry Foundation classes. As you know, it is an international standard, and it provides an open and neutral data format. So we actually do have a format that we have agreed on to share and share information. However, the problem with IFC is that it is very its schema is very large, it's very complex, and it's continuously evolving. And once you try to get into the specific semantics, it becomes rather difficult to abide by the specific entity or relationship that it needs to be assigned to make sure that interoperability issues don't occur. So to give you a simple example, for example, in this diagram here, what we could coarsely describe as beams can be subdivided as planks. It can be a plate. What we see as just a column can also be expressed as a post or stud walls or parts of a stud wall. So it's not that easy to assign the correct IFC entity to a very detailed BIM corresponding element. Another example I like to give sometimes is what we call this. It's a, in English, I believe it's called a concentric plug. In Korean, it's called Concentric. In Japan, I think it's similar, Concento. So in English, you also call it an electric socket. So in the IFC world, what is the correct terminology or entity that we need to assign to this BIM element? Is it a concentric plug or is it an electric socket? And if you search, the actual answer is IFC flow terminal. So the point is that unless you are very an expert in IFCs and have dealt with it many a times, this can be a bit confusing, and it undermines the initial paradigm or objective of using IFCs. So the goal of one of the goals of my research was to try to use AI, artificial techniques approaches, to check whether specific BIM elements in a BIM model correctly correspond and are mapped correctly to its associated IFC entity. Now, existing research used to use a inference rules-based approach, but more recently, researchers have tried to use AI and machine learning approaches to check for these mapping associations. So what we've done thus far is to look at different machine learning and also deep learning approaches that would be the best classifier for looking at a BIM element and detecting whether that element is, for example, a door, a window, a beam, or a column, or so forth. And so we looked at some deep learning models such as MVCNN or multi-view CNN, PointNet, support vector machines, and so forth. And we've come to the conclusion that multi-view CNN was the most fit and had the best performance in classifying these individual elements. And MVCNN, what it does, basically it looks at a 3D element like here, and then it takes pictures from all sides, and it takes pictures, 12 images, and then for each image, it uses a convolutional layer to determine its features, and then it joins all those learned features in a view pooling layer, and then uses a second CNN layer to determine whether indeed this is a window, or a curtain wall, or a door, etc. So we've had some good performance, but MVCNN still did have some limitations, and in other words, it still had some errors in classifying certain elements correctly. So we looked to see what were the reasons for that limitation. And we discerned that one is that we didn't have enough training data, so we need more element samples. And the second is that the images that it uses to learn, the lack of definition or sharpness in its resolution was also a reason that it could not classify some elements correctly. So this research and this presentation is about how we try to improve the performance of MVCNN by one, increasing the data sample using data augmentation techniques, and two, using a semantic segmentation technique which basically tries to sharpen the resolution of individual images. Okay, so first, to increase the size of the samples, we sourced BIM models and also libraries from open source websites, and we were able to collect about 12,000 elements. And then we use parametric modeling, specifically Dynamo in Revit, to actually make dummy elements by randomly tweaking the parameters of the individual BIM elements. And finally, for 13 elements, we were able to make 4,000 elements, which totaled 52,000 data sets. Okay, and then the next step was then for each of these 52,000 elements, we converted them into each of 12 images to get about 624,000 images for our whole data set. Okay, and then we use that data to put it in our multi-view CNN and to see how good it could classify the individual elements here. And the result is pretty good in that its classification accuracy was about 95%. And you can see that the individual accuracies are pretty high, apart from a few types such as walls and windows, which it still had trouble in accurately classifying. Okay, so then the second step was again to use semantic segmentation to help with image resolutions and to help it to discern the image boundaries between the background and the actual element itself. And so semantic segmentation.
You have 1 minute.
Okay, so semantic segmentation is a way to divide the pixels into individual objects. And then we used the most up-to-date semantic segmentation approach, which we call CRFN. So I'll just jump over these. And then we use that to sharpen the individual images as previously I just said. And then you can see as a result that improvement was about 4% in total. And it particularly had allowed wall and window elements to improve. Okay, so just to give you an example, so previously it would classify this element like as a beam, but now because of using semantic segmentation, it has classified it correctly as a wall. And previously this was misclassified as a curtain wall, but now it correctly classifies it as a window. Okay, and finally, we actually uploaded into a REST API server so that it could actually you can actually do the classification on a commercial software. So since I'm out of time, I'll just skip over and go to the conclusion. Okay, so in conclusion, we were able to improve the performance of the MDCNN deep learning model by about 3.47%. I know that doesn't look very high, but actually in artificial intelligence, getting a 95% accuracy and then trying to improve that to 96, 97, or 99% is the last mile, which is a very difficult task to achieve. So we are happy about that, and we still have some limitations that needs to be improved, but we also uploaded it to a commercial software so that it can be used in a cloud-based fashion. Okay, so